I'm going to be talking today, with a few slides on decreasing the risk of Iran's 5% enriched uranium hexafluoride stockpile using reprocessed uranium. It's kind of something that people have been thought about in the past, but we're going to apply it particularly to the Iranian case, and it's based on some research that I'm doing. It's part of science, what I call dry science. There's wet science, which is what I used to do as an experimentalist, which is working in a laboratory and doing experiments. And then there's something I call dry science, which we are doing here at CNS and at MIIS. And that's the idea of doing science as applies to arms control and non-proliferation, but not having a lab access to do it. So there is things that you could do just with a pen and paper and a very good computer. And of course, now that I think we are very, very close to an agreement with Iran, this is more or less just a Gedanken experiment, a thought experiment. But it may have applications in the future for other purposes. So it's rather detailed, and I'm sorry, I'm going to go into quite some physics detail. But I'll pull you all along, and I hope I still make it relevant for you. So the question is it either a detailed Gedanken experiment, so really a lot of work, or is it actually a good idea? That's something we'll see in the future, I guess. Okay, so the main idea is to use something called reprocessed uranium. So reprocessed uranium. That's uranium that's been basically fuel itself, fuel from a reactor, that's been processed, and the uranium has been taken out from the fuel. That uranium has some properties that's different from natural uranium. It will contain isotopes like uranium-232. So this U-232 corresponds to uranium-232. So I'm pointing to a particular isotope, uranium-232, which has very different properties from the other isotopes that you're used to, uranium-235 and uranium-238. So the questions I'm going to be answering is, how can reprocessed uranium, so Rep-U corresponds to reprocessed uranium, can reprocessed uranium be substituted for uranium in Iran's 5% UF6 stockpile? So as you know, with Iran has produced a large quantity, 7950 kilograms of 5% enriched, U-235 enriched, UF6. And this is a concern for P5+1 and a lot of people in the non-proliferation community. And the question is, can you convert that 5% stockpile into some material that can't be used for a nuclear weapon? Use it for nuclear reactors, but not for nuclear weapons. That's really the question. And if so, how much U-232, which is part of reprocessed uranium, how much U-232 would you have to add to basically denature? Now we're getting to the word denaturing, which I'm going to be talking about, the UF6. So how much U-232 is needed at 5%, so that when it's enriched to weapons grade, which they wouldn't be allowed to do, that material would essentially be very bad to build nuclear weapons out of. That's really the idea here. So how much U-232 do you need to add at 5%? So when it's enriched to weapons grade, that's 90% plus. It effectively denatures UF6, or makes it useless for nuclear weapons, or less useful for nuclear weapons. The interesting thing, though, is that uranium-232 enriches with uranium-235. You know, through the process of enrichment, you're increasing the proportion of U-235 compared to all the other isotopes, right? The interesting thing is that if you have at 5% a certain quantity of U-232, if you enrich that 5% to 90% U-235, then that U-232 increases in concentration with the U-235. So you have a bonus there. So that the more you increase, the worse it will be for nuclear weapons, because you don't want to have U-232 for nuclear weapons, and I'll explain why that's the case. Basically, the idea is that any neutrons, any excess neutron, can cause pre-detonation of a nuclear weapon, which is what I'm going to be talking about briefly. And basically what we'll do is we'll do calculations assuming certain impurities in the fuel present in the metal itself, so that's weapon-grade uranium, and see how that affects, how well the material is denatured. Okay, so that's the main idea. The analysis process is a little bit complicated, unfortunately. We start with the idea that you have a gun-type bomb. In a gun-type bomb, what you don't want to have is excess neutrons. if you have access neutrons before the material is assembled, if you kind of understand how a gun-type bomb works, you take two materials that are close to critical mass, and you bring them together very fast so that they form one critical mass, essentially, or a little bit more than a critical mass. At that point, the chain reaction starts. Now, if these two materials are coming together, close together, but they're already starting to have neutrons and start the chain reaction, when they get together, they can't get to the yield that they need to get. And really what you need to have for a gun-type bomb is you need to have 1 millisecond, essentially, 1 millisecond window in time where there's no extra neutrons. Okay? There's no extra neutrons there. And that's what you have with some materials, is that you can trigger it exactly at the right moment when they're assembled, the two critical masses are, or two materials are assembled together. That's what you want for a good bomb, or for a bomb that works, that doesn't pre-detonate. But if you have materials that come together and start to disintegrate as they're coming together, you can't get to the assembled mass that you need to get to have a proper to get the yield that you need to have. And if you think about that window in time where you need a millisecond where there are no neutrons, right? If you happen to have materials that have neutrons, then you can't have that 1 millisecond window. And so that's the idea, that this uranium-232 or reprocessed uranium adds neutrons at the wrong moment in time. So you can't get to that assembled state. So we're going to look at the properties of reprocessed uranium then. How this U-232 produces neutrons. Well, it produces neutrons in two ways. One is just through spontaneous fission, which is just same as the normal fission process, but this just happens a kind of decay process that the isotope has. And then we'll find that uranium fuel, and this was a surprise to me, that weapon-grade uranium has impurities, and these impurities also cause neutrons. And it turns out, according to my calculation, that the neutrons that you get from impurities that are present in the metal itself cause way more neutrons than the neutrons from spontaneous fission. So this is the analysis process. We'll find that 100 ppm uranium-232 basically turns weapon-grade uranium into, that you can actually denature UF6 when it's enriched to, so basically you can't produce a bomb, a gun-type bomb out of reprocessed uranium if you have this much 100 parts per million uranium-232. We'll go through that and explain it a little bit more as we go in. So that's kind of the general analysis. And then we're going to apply it to the case of around 5% stockpile. So that's the two phases, two parts. So first we're going to see, and that's the whole point, we're going to see how much uranium-232 do you need to effectively denature the material, right? And then we're going to see how much do you need to add then to the uranium UF6. First you have to, you have the 5%. First what we do is we blend it down to 3% with natural uranium. So blending it down means basically you're adding uranium-238, natural uranium, okay? You're adding natural uranium. You blend it down to 3% U-235 enriched material. Then you blend it up, but you don't blend it up with higher enriched material. You're using, instead of using natural uranium, you're using this reprocessed uranium. We'll go through that, and then the whole point is then how much material do you actually need to add to get to the level where you cause this denaturing of the material. Okay, don't worry if you're confused now. I'm going to take you through the different steps. We'll start with the idea of denaturing. What does it really mean? So the definition is that process of artificially changing the natural isotopic composition of a chemical element in order to give it new desirable properties. Or in the case of denaturing uranium, in the case of denaturing alcohol, you give it other properties. Let's say you're talking about alcohol. You give it other properties that make it not nice for consumption. So you make it smelly, or you add other materials that make it even poisonous, that kind of stuff. So alcohol is not just for consumption, as you know. In fact, it's a very small slide. Well, I'm not sure if this is exactly right. This is kind of this pie graph here. But you have a certain portion which is alcohol used for consumption, and that's controlled, right? But then you have a whole other applications for alcohol, for cleaning and this kinds of stuff, right? That you don't want to have controls because you want it to be widely used. And that's really the idea here, is we want to have this kind of material for the uranium point that could be used for reactors, but not be used, basically poisonous, for nuclear weapons. That's the idea. Can we get there? So what did I want to say? So the material that you're using for, I was talking to the alcohol case itself. Alcohol that's not used for consumption has many other purposes. It's still simply alcohol. It's still alcohol. They add something to it to make it less interesting, or make it bad for you, or something like this. Right? It's an additive which makes it less appealing for consumption. And that's the idea that I'm applying denaturing of UF6, making it useful for nuclear reactors, hopefully, but less useful for nuclear weapons. That's the idea of denaturing. So, just like I said, alcohol is not just for consumption. Uranium is not just for nuclear weapons. It's also used for nuclear reactors. So the question is it possible to denature uranium in the same way alcohol is denatured? That's really the idea here. So let's assume a quantity of weapon-grade uranium so that the fraction of U-235, right, the one that's very useful for nuclear weapons, compared to the other isotopes, are greater than 90%, right? That's basically weapon-grade material. What could be added to weapon-grade uranium to denature it? So that's a question. What could you add to weapon-grade uranium to denature it, essentially? Does anybody know? Just U-238. That's the idea. You're turning the HEU into LEU, essentially, right? So you're converting it. You're changing the proportion of U-235 compared to U-238, basically, of U-235 and other isotopes. But basically what you're doing is you're adding U-238. Why? Because U-238 has a lot of neutrons. So you ruin its use for a gun-type bomb, say, for example. That's the idea. So let's look at the properties of less than 20%. So in this case, you have LEU, which is less than 20%, right? In this case, the critical mass at 20% is 15 times the critical mass at 90%, which is one complication if you want to build a nuclear weapon out of LEU. But the neutron rate is much, much higher, since if you compare U-238 versus U-235, 1,200 times the amount of neutrons are produced. And remember, as I said, with pre-detonation, you don't want to have the neutrons, right? And what we're doing is we're forcing neutrons to be in the material to cause it to pre-detonate if they enrich it to weapons grade. Okay, if it's still confusing, don't worry, I'm getting there. I'll make it simpler. So just this is from Alex Glazer in Science and Global Security. If you look at the probability, remember I said you need to have this 1 millisecond time where you have no extra neutrons. You have the window in time where there's no extra neutrons. If you have a high percentage, a high U-235 enrichment, right, then you have very little U-238. And remember I said U-238 is the cause of all the neutrons, right? So that's why you can have a high probability that you have this neutron-free window. But if you decrease the enrichment from 90-something% all the way down to 20%, suddenly you have a whole lot more U-238. And the U-238 is what gives the neutrons. And yes?
Is it okay if I ask?
Yes.
So how does 238 give neutrons?
So through spontaneous fission. And so it has a much higher amount of neutrons per gram per second compared to U-235.
So the 238 actually undergoes spontaneous fission. Sorry, I'm
yes. No problem. Yes. And it goes much more, so it gives off many more neutrons compared to U-235. So if you increase the proportion of U-238, then you have many more neutrons, and you can't get that little millisecond window where there are no neutrons. That's the idea. Okay. So you go down here, you're increasing the U-238 fraction, right? Because it's U-235 versus divided by U-238 essentially, plus the other isotopes don't count so much. Okay, so you increase the U-238, and so here, a 1 millisecond assembly time is basically not possible. So you can't really build nuclear weapons out of LEU in that case. for an assembly time of 1 millisecond. So what happens if the assembly time is decreased? If you decrease the assembly time, now you're going from gun-type weapons to, say, an implosion design that you've heard of before. There, instead of being a 1 millisecond time window, the time window is much shorter. It's more like 10 microseconds. And in that case, the probability of a neutron-free assembly time increases. So again, as you get to low enrichment, it's still useful for nuclear weapons, but there's other complications with building implosion weapons out of LEU. Okay? So this is the one thing. So uranium is downblended, less than 20% is basically not possible to use for a gun-type bomb. That's really the conclusion here when you look at that graph in terms of the probability. And it's difficult to use for an implosion-type bomb. But you could enrich that material further, right? If you have LEU, this is our concern with Iran. If they had 20% material or 5%, it could be enriched further to weapons grade and be used for a nuclear weapon, right? So that's a concern. So it's not quite the same as calling it denaturing. That's my point. It's proliferation resistant, but it's not proliferation proof. What you really need is you need to have so many neutrons being produced that it makes it very difficult. You could still use it for nuclear reactors, material for nuclear reactors, but makes it very difficult to use for nuclear bombs because you don't have that neutron-free window in time when you assemble the weapon. So you need to, putting it in another way, is you need an additive that increases the number of neutrons per gram per second. That's not easily removed. Okay, you need to add something to UF6 that's not easy to remove, and produces a lot of heat. If you produce a lot of heat through alpha decay, then you're making it difficult for high energy explosives to be surrounded because they're going to start to melt, and you're going to get into all kinds of difficulties there. So when I look at the candidates, uranium-232 is pretty good. It's got 1.3 neutrons per gram per second, or 190 times more neutrons than uranium-238. And U-232 appears in reprocessed uranium. So then the idea comes, and you could just substitute uranium that you have normally, right? Substitute it with the same enrichment, 5%. Let's say you take the uranium 5% enriched material, substitute it, but instead of it having U-238, regular, just been made with natural uranium, you mix it with reprocessed uranium, and that's the idea. So the U-232 causes a lot of neutrons, which make this time window, 1 millisecond, very difficult to achieve, even at weapon grade, when you're enriching to 90%. That's the idea here. U-232 is basically produced when normal uranium fuel is irradiated in a reactor. Then you're producing U-238, U-236, U-232, and also other isotopes. So that's part of the uranium fuel. Normally, if it's fresh fuel, you wouldn't have the U-232 there. Okay, so you wouldn't have that. You wouldn't have the U-236. You wouldn't have the U-232. You only have that when you place the material in the reactor, radiate in the reactor. So this is an idea that's proposed by the Russians. My idea is not original. It's proposed by several people. And here are some nice links to some very interesting papers. So first, let's now talk about getting U-232. You need to reprocess the uranium fuel. And you have the Purex process. You have different types of processes for this, which is that you separate the uranium, the plutonium, all the different materials from the fuel. So the fuel goes into the reactor. So this is fresh fuel. Goes into the reactor. It's used for several years. That depends on the reactor. And then it comes out as spent fuel. Spent fuel is hot and radioactive, has plutonium in it, has uranium in it, and many other different isotopes. And you have to separate the uranium from the plutonium and then all the other materials. And this is what's done through the Purex process. And there's different types of reprocessing processes out there that do this. Now, if you separate out the uranium, let's say that you do this, and the Russians do this, and really focused on the Russian case, which I will talk about. Uranium contains U-232 and U-236. Now, U-236, so that's the other isotopes that's present, is actually not so good for nuclear reactors. And this is a problem with this method. If you look at the different IAEA reports, of course, there's proponents for using reprocessed uranium for reactors in Japan and in many different countries, in Russia. If you just substitute enriched natural uranium with enriched reprocessed uranium, so it's not using natural uranium, but it's using reprocessed uranium instead of the natural uranium, then you need a slightly higher enrichment, about 14% or 12% higher enrichment, to compensate for the fact that you have this U-236, which just absorbs the neutrons. So to compensate for the U-236, you need to increase the enrichment. But if that's all it is, then it's not such a big deal. The problem is, that's not all it is. It's also this fuel, then, if you use reprocessed uranium, is going to be quite a bit more radioactive because you're adding this U-232, gives off a lot of neutrons, gives off a lot of alphas, a lot of other particles and so on, and that means it's going to be more radioactive. So if you're asking somebody to use reprocessed uranium, then you're also asking them to deal with the fact that if they make fuel out of it, it's going to be more radioactive, so they have to actually manage that, and that's not necessarily so simple. And that's one of the drawbacks of this method. So what are some of the advantages of the U-232 additive? So U-232 decays, so it changes from one isotope into another isotope in many different ways, through what I call a decay, what's called a decay chain. So it goes from uranium-232, which has a 69-year half-life, to thorium-228, then blah, 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 to radium-224, and then quickly through these four, and then branches up here into 64% going this branch, and then 36% going this branch. Doesn't matter, don't worry so much about it, but at each step here, the red arrow, it's giving off an alpha particle. So at every U-232 decay, you get this string of other alphas, and this makes it more radioactive, but as we'll see, it also has some very good properties. And it's an advantage which I didn't think of before. This decay process is some of the students, people who are students in my class know, I like to think of them in terms of buckets, right? You have a certain amount of U-232, and that goes into thorium-228, and then that, you have different size spouts, depending on what the half-life is. Then it'll go into the next bucket, next bucket, next bucket, next bucket, and so on. And you can see here, what's happening is it goes very fast to these, or sorry, I didn't show you the time here. It's because it's very, very short, much shorter than even this or this. Okay, so it goes straight through. As soon as, a little liquid drops into the bucket, it immediately falls out to the next bucket. You guys see what I mean? But each time that this happens, you get an alpha particle being released. And that's really the trick here. I've done simulation where I calculate how many, as a function of time, how many of these alphas get produced, essentially. When you get this decay, U-232 decays through all this chain, you get a whole bunch of different isotopes being produced, and you get a certain amount of radioactivity, and that's being shown here. Now, this is very important because it shows you how many alphas are being released. And I'll show you why this is important. There's a method to my madness, don't worry. And that is, you get neutrons, because remember, what we want to get neutrons. Right? We want to have as many neutrons as possible to force this thing to pre-detonate if you have a lot of U-232. So we get U-232 through spontaneous fission. Remember, there's 1.4 neutrons per second per gram of U-232. So we get a lot of spontaneous fission, but I'm afraid it's not enough to cause a pre-detonation. But what you have is that uranium metal, as manufactured, has many impurities. So I went and I looked at some of the Russian companies that manufacture uranium weapon-grade metal, and I looked at what kind of impurities are present. And what surprised me is that there were a lot of different impurities. So this is ppm, or parts per million. 1 ppm is equal to 1 times 10 to the minus 4%. Okay, so it's small, but it's not that small. So this particular isotope is fluorine-119, about 350 ppm, carbon-13. So this is carbon, so this would be the elements. Carbon-200 ppm. These are all the different isotopes, as you can see here. And I assume that these are the impurities from the Novosibirsk chemical concentrates plants. So this is the information that we have on the weapon-grade metallic uranium. Okay? So why do we care? Because each time an alpha goes, an alpha can hit these impurities and produce a neutron. So depending on how much material I have of these impurities, it affects how many neutrons I get out. And it turns out you get way more neutrons because of the impurities here than you do from spontaneous fission itself, which is surprising. So the goal here, and I'm going to take you through this, is to calculate the contribution of neutrons from alpha N, this reaction where the alpha gets absorbed by the impurity and then gives off a neutron in response, from the impurities in the material. And now I know this formula looks complicated, but I'm going to take you through this nonetheless, right? The idea here is to calculate what's called the thick target yield, or basically the number of neutrons per alpha. And if you look here, this is the expression, which has the energy of the alpha, the threshold of the reaction, has which is called a cross section, and I use different codes and sources for being able to get all this information. And then you have something called the energy loss. Okay. Now, if you think about it, and there's also the concentration of the impurity. That's obviously important because of the number of targets that you have that the alpha hits. If you think about the ingredients for this thick target yield, as I call it, the ingredients that we had here all make sense. So I'm not going to derive this. Okay, don't want to waste your time. I'm not going to derive this, but it's important to kind of see why these ingredients are there and that they kind of make sense. If you think about an alpha passing through a certain material with impurities, in this case it's uranium metal, right? If you have a very low density impurity, then as the track goes through, this is called an alpha track. So the alpha particle goes into a certain length, essentially. It's called a track. Certain length to the metal. If you have, and these X's represent where the low density impurities are. If the density is high, right, then it's going to hit the impurity. So the chances are higher. So obviously, it's going to depend on the density of the material, right? The density of the impurities, how many impurities there are going to be. It's also going to depend on what's called the cross-section or the sigma variable. You often see this in the literature, right? The sigma, which is basically, you can think of as the probability of the reaction happening. So the probability of an alpha being absorbed by the impurity and then giving off a neutron, right? That's called the cross-section. And you can think of the cross-section as kind of the size of a target. I always talk about it this way. If you have, cross-section is actually measured in, it's cross-section, right? It's measured in the size of something. It's how big the impurity nuclei actually looks from the point of view of the alpha, to actually undergo the interaction. So if that was a very small dot and the track is going like this, it's going to miss it. But if it's a very big, if for the alpha particle goes through, that target looks really, really big, like this one, it's going to hit it. And that has everything to do with the nuclear physics of cross-sections, as we'll talk about. So, and the other thing that's important is the EDX, which is the energy loss. Of course, as the alpha particle goes through, it's going to lose energy. And so depending on the energy, this cross-section or this probability of the reaction is going to be lower or higher. It actually depends on the energy. So of course, energy loss is going to be important because as the alpha particle goes through the material, it's going to lose energy. And as it loses energy, it's going to have a different energy. And so the cross-section is going to be different. So all these ingredients that I have here, the energy of the alpha, the EDX, which is just energy loss, so how much energy the alpha is losing, and the number of target nuclei, all kind of make sense, even though I haven't derived the expression for the thick target yield. So for this case, fluorine-19, this particular isotope that I looked at, you can see how the cross-section varies. So this is in this very funny expression called barns. Physicists use these strange terms. A barn is actually very small. It's 10 to the minus 24 centimeters squared. So we're talking a very, very small little cross-section. But you see that probability, you can think of it in terms of probability, increases as a function of alpha particle energy. So if you have a very high energy alpha particle, right, and it loses energy as it goes through the material, at very high energies, that cross-section or that probability of interacting with the impurity is going to be higher. You need to take all that into account. So this is this expression of the cross-section for fluorine 19. Now if I flip that, so basically what I did is I took that graph and I flipped it the other way. So now I'm starting at high alpha particle energy and I'm going to low. Then it starts to make more sense what's really happening. So the alpha is born at something like 6.5 MeV. It starts out here. At this point, it has a very high energy. So it's very easy for it to interact because that cross-section is very high, right? This is very high. So it's like a big target, right? But as it's losing energy, as it traverses through the metal itself, now it's getting smaller and smaller and smaller because you saw that cross-section is going down here, right? This cross-section is going down. And then at one point, the reaction stops at 3 MeV, right? And now you don't produce any neutrons anymore, although it'll still lose some energy as the alpha travels through the material. Okay? So all that information I'm using to calculate how many neutrons I get per alpha, essentially. So, and the other thing you need to calculate is the energy loss of an alpha particle through uranium metal. And I use a program called SRIM 2008. It's kind of a standard material program for calculating the energy loss. And you see how that changes as a function of the alpha particle energy. So now you see we have all the information that we need to do this integration, right? We know how the cross-section varies as a function of energy. We know how the cross-section varies as a function of energy. That was that falling down curve, going up 0 to higher energies. And then we know what dEdx is, right? Because that's what this is. And we have all the information out. Now we can actually do the integral. Right? So it's an example. Now we do this integral with radium-224, which is one of the isotopes that this went through in this decay chain. It's one of the daughters of U-232, which has two alphas, one at this particular energy, 5.684 MeV, and one at 5.448 MeV, which then is averaged. I took some simplification. I average it to one particular energy alpha. Okay, so now I do the integration for that particular alpha all the way down to 3 MeV, which is where that reaction stopped. Follow what I'm doing? So, and that's only, of course, for fluorine-19. I have to do the other isotopes as well, the other impurities that are present in the uranium metal. So the result is the number of neutrons per alpha for fluorine F19 target. Now I have to do it for all the alphas, right? Because there were other alphas there. There was thorium-228, polonium-216. All those different alphas all have different alpha energies, and I have to repeat this calculation for all these different alphas. Okay, so now if you calculate all this out, this is generally, right? You have something like 10 to the exponent 12 alphas per gram per second. So you have a lot of alpha particles now. If you have that number, then the neutrons per alpha times the number of alphas per gram per second, these alphas cancel, and you get the number of neutrons per gram per second, which was exactly what you needed to have. Okay? That's just for fluorine-19 and all those alphas. You still need to do it for all the other isotopes. Right? So you need to repeat this process for all the different impurities that are present in the metal, which I did. And what you get is very interesting. You get a high number, much higher number than I expected, which was 324 neutrons per second per gram uranium-232. That's basically the result of this complicated calculation, because I can now add this to that 1.3 neutrons per second gram per second here, due to the from spontaneous fission, right? So I just simply add these two. Well, actually, it's dominated. And here, actually, what I did is you can see this is this 1.3 and this is this 328. Basically, everything is due to the impurities that are present. All the neutrons that are there are mostly because of the impurities that are present in the metal. So one question is, can we add other metals to the materials, other impurities to the metal to cause predetonation if there's too many neutrons around or too many alphas around. So you see that it's really, basically spontaneous fission is the effect from impurities is way more than spontaneous fission or any other neutron source. For fun, I calculated what it is from cosmic rays. It's also way, way, way smaller. So I calculated then how much you can then calculate how much U-232 you actually need to cause this predetonation, to make the probability of predetonation higher, so that you don't have that 1 millisecond free where there are no neutrons. Just follow me. And what you see is just, this was the original curve that I used for natural uranium, or uranium with with different enrichment but using natural uranium. And this is if I just add 100 parts per million uranium-232 to the material. Okay? And in that case, you have so many neutrons that it becomes very hard to have a 1 millisecond window where you have no neutrons, which makes predetonation much more likely. So effectively, if you have this 100 ppm U-232, for long assembly times, you're denaturing the material. Because if at weapon grade you have something like 100 ppm, then you can't really use it for at least a gun-type bomb. Okay, so that's kind of the first important result. But manufacturing a bomb with weapon-grade reprocessed uranium is hard. The predetonation probability is going to be higher because we're assuming a very long assembly time, the 1 millisecond assembly time, as you saw from the previous graph. There's also, because there are many, many alpha particles, it's going to produce a lot of heat. This will heat the high explosives, but I found, unfortunately, that it doesn't seem to be high enough to cause real problems with sophisticated high explosives. And I'll get to that a little later. And there's going to be many, also the alpha particles themselves are very energetic, and they destroy the UF6 themselves. And I did a calculation, but I'm not really confident enough to present it here. But I did a calculation of figuring how many UF6 molecules would be destroyed per alpha particle. And so if you know the number of alpha particles, you can figure out how many UF6 molecules will be destroyed. So basically what happens is the alpha particle is very energetic. It's like a little bus. It slams into UF6. If it's UF6, not metal, right? If it's not metallic uranium, it's UF6 form. The alpha particle slams into UF6 molecule, breaks it apart, and so you have a broken UF6 molecule, and you can't enrich further. So that's something that I have to look in further, is how many alpha particles would you need to basically make enrichment of UF6 very difficult to weapons grade, because with the alpha particles, you're destroying the UF6 as you go along. Okay? So that's another issue that's important to think about. The other issue is the gamma dose. So if you took, so gamma dose means the dose that you get, basically radioactive dose that you get, to yourself, if you were working with this material. What you want is for that dose to be so high that nobody will even want to touch that material, right? As another way of denaturing it, right? If you get close to the material, you'll just get irradiated, and you'll get all these gamma rays, and it'll be very bad for you. So that's what you would like to have. And I calculated what the gamma dose is from 5 kilograms of uranium metal. So let's say you have 5 kilograms of uranium metal as a sphere in front of you with 100 ppm U-232, and it's very, very high. In less than 2 hours, you get the dose annual allowable exposure for radiation workers. Okay, so less than 2 hours exposure, that's at 1 meter distance. So it's going to be very radioactive, and nobody will want to work with the material. It's going to be very difficult to work with. So that's another approach to denaturing. When it's not enriched to weapons grade. So remember that I said that U-232 enriches with U-235, right? And going from 5%, say, to, let's say, 100% or 90%, that's about a factor of 20. So you're enriching the concentration, you're also increasing the amount of radioactivity. So if you then go down to 5%, right, you're basically, the dose that you get is going to be down by about a factor of 20, right? Because you're enriching the U-232 with the U-235. So if you go down to 5%, it's not going to be nearly as radioactive as it is at 90-something percent. And it's because it's not as radioactive, it might be more manageable in terms of dealing with the material. So then, if you think about 3 to 5% being used for nuclear reactors as fuel, as being reasonable to use for nuclear reactors, then maybe you could manufacture fuel when the dose is low enough so that you can manage it. Of course, if you ask the Iranians, they say, well, if you're forcing us to do this, you're not forcing other countries to do this. So why should we use material that has higher radioactivity than if it was just natural uranium? That's another issue we'll talk about a little later. So the goal is that at U-232 at 100 ppm for weapon-grade uranium seems to denature the material for a gun-type bomb, okay, at 100 ppm. At 5%, what's the concentration going to be of the U-232? And I introduced this variable gamma, which is basically just a factor in the reduction in the concentration. It's no surprise that, so I did a calculation using, if you're interested in this, there's a particularly very good paper, which is multi-component isotope separation cascade, composed of elements with large separation factors by Yamamoto and Kanagawa, where they have an algorithm which allows you to actually calculate how the enrichment actually proceeds when you have something other than just U-235. You have U-238, U-232, U-234, and many other different isotopes. And also there's actually a calculator where you can look this up. But what I want to say is I calculated that the way U-232 enriches is about a factor of 19. So, and it's not such a surprise because if you think about 90 divided by 5 is about 18. Right? If you're going from 5% U-235 enriched at 5%, then you go to 90%, that's 18 times more. Right? So U-232 is pretty close to U-235, so you expect a similar factor of about 18 or 19. And according to my calculations, it's about 19 in this calculation. So we talked about the top part, right? How we go to calculate how many, what concentration of U-232 we need at weapons grade to basically make the material not useful for a nuclear bomb using a long assembly time of 1 millisecond. Okay. Now let's apply it to the Iran case, right? I've applied it to other cases too, but let's apply it to the Iran case in this case. And what we're going to do is we're going to determine the blend stock, basically the enrichment that you need to do. You need to blend the material with, and how much U-232 you need to actually enrich it to 5%, so that when you enrich that further, you get the effect that you want to do. I know it sounds confusing, but I'll take you through this now. Okay, so as you know, this was the latest IAEA report. Iran has 7952.9 kilograms of up to 5% uranium-235. I assume basically 5% U-235 for my calculations. And when I go through my calculations, what I find is that this factor of gamma 19, and I'm going to talk about that later, but that's kind of important. Okay. So I propose kind of a two-step process in this case. It's not complicated. The idea is that we start with the 7950 kilogram near 5% UF6. We blend it down to 3%, and you need about 6950 kilograms natural UF6 to be able to do that. So now it's down to 3%, right? The material is down to 3%. Obviously, the Iranians are not going to be happy with that. You blend it up, but with reprocessed uranium, back up to 5%, right? With this much, 2930 kilograms of 70% rich UF6 with 30 ppm U-232 to get to the 5 ppm that you need for at 5%. Because if you take the 5% and you enrich that further to weapons grade, you get to the 100 ppm that you needed for denaturing the material. Okay? And so the idea is that if you have this, if you enrich this to, if you use this mix where you're mixing the 5% with 2930 kilograms, 70% UF6, with 30 ppm U-232. Then you produce enough material at, you basically produce 5 ppm U-232, which is not usable for nuclear weapons if you enrich it further to weapons grade. But you can use it now for reactors, and that's really the idea, although it's going to be more radioactive because you do have that U-232 additive. These red parts here, of course, require some more math. That's why I just go through quickly. Basically, the idea is that you use something called mass balance, which is not hard to understand. Whatever you put in, you get out. And when it comes to concentrations, you have exactly the same thing. So you have a certain product here, which is the feed material plus the blended material. And this XP here represents the concentration of uranium-235, okay, for the product. And this is the feed, and this is the blended material. So X's here represent the concentrations of U-235s, and the X primes represent the concentrations of uranium-232. Okay, both are important in the final analysis. And let me get ahead of myself. So again, the idea is that we just take a certain amount, this is 7952 kilograms of 5% UF6, uranium UF6. We mix that with natural uranium, right, which has an X, so this is B1, right, stage 1 blended material. It's got a concentration of 0.071, which is this natural uranium. We're mixing that with material to get 3% product. And you can go through the calculations of how to do that. And then what we do is we take that material from stage 1. So that's the first part where we blended it down to 3%. Now we're going to bring the 3% up back to 5%, but we're going to use reprocessed uranium. And for this case, I used the Russian, throughout the whole thing, I've been assuming there's Russian material. Russian blend stock at 70% LEU, but then with the light element impurities that I had before when I did this calculation. And I bring it up to 5% LEU, where the U-238-32 concentration is 5%. And again, the reason why the U-232 concentration is at 5% is because if I enrich it further, I'll get to 100 ppm, which was enough to denature the material at weapons grade. That's the idea. But at 5 ppm, it may be still useful for, it's not radioactive enough that you can't use it for nuclear reactors. Okay? Now you get this idea about this denaturing idea, right? The idea is that you have a controlled area, which is, like alcohol. That's controlled. We can't easily just go into stores and buy alcohol. But then you have all the other applications for alcohol, right? Which doesn't need the same kind of control as the other material does. And so the idea is that if you have this material, which could be denatured with 5 ppm U-232, then that material wouldn't have to have the same kind of controls or safeguards as you would have with other material that doesn't have the U-232 in it. That's where I'm going. So we find that at 70% U-235 feed, we require about 30 ppm U-232 in the blend and 2980 kilograms of reprocessed UF6 to get to that point where you have this nice 5 ppm material, which, when it's enriched further to weapons grade, will be enough to denature the material. So, can denaturing of UF6, and getting to the end here, can denaturing of UF6 be done? Well, 30 ppm U-232 UF6 can be mixed with blended down 3% UF6 to produce 5% UF6 with 5 ppm. I know, it's a big mouthful, but I hope you're getting the idea here. The material will enrich with the factor gamma, which is this 19 factor that I found for this material. There's many questions I still have. Need to determine whether getting 30 ppm U-232 is feasible for reprocessed uranium in the first place. And Margarita and I tried to contact some Russian scholars, and we didn't have much luck getting that information. but I hope to be able to get that. I found that the gamma dose from, say, 5 kilometers, sorry, that's not 5 kilograms weapons rate, that's 5 kilograms, that's at 5%, so 5 ppm. And in that case, it's much, much more reasonable material. Remember I said that less than 2 hours is enough at weapons grade to seriously cause trouble to you? Here, it's more like a 35-hour direct exposure. So you could handle that with shielding and so on, although it will be, a lot more work and a lot more effort. But as I say, I say this is manageable, but Iran would probably say, and I talk to my friends, say other countries don't do so, so why should we? Right, so that's one thing you would deal. That's why I call this a Gedanken experiment. It's a thought experiment because I think in reality it wouldn't work this way. But in the future, there maybe there's applications where this would be useful. Now, what about if you had a very short assembly time? I talked about long assembly time, which is gun-type weapons. What about implosion-type weapons, where the assembly times are much, much shorter, more like 10 microseconds? In that case, denaturing will not work, which is really too bad. So this is with the short assembly time, which is that 1 millisecond window that I talked to you about. This is where it's 10 to the minus 5 seconds. And you see that the probability is still quite high for an assembly time, in this case 10 microsecond window, where you have no neutrons. So the 100 ppm probably will not work for implosion weapon. You probably need to have more, a higher concentration. That's what I'm saying. I also looked at how the heating, the effect of the heating by the alphas. I found that if you look at the heating of the alphas, of all these alphas from U-232, and you compare it to the heat from plutonium-238, because people often talk about plutonium-238 as producing a lot of heat, it's 20 times more, so there's a lot of heating. But since you're only looking at about 5 ppm, or in this case, if it's weapon grade 100 ppm, there's just really not enough of the material present there to cause enough heating to basically melt to disrupt the high explosives. But that deserves more care in the calculation. I just did a rather simple calculation. I found that the surface of the uranium sphere, so I looked at basically sphere of uranium, only increases by 20 degrees Celsius, which is not enough to melt low tech, which is low tech explosives, countries that have low tech, but 80 degrees Celsius or medium tech, which is 190 degrees Celsius explosives or more. So, just in conclusion, denaturing UF6 reprocessed uranium for long assembly times, it is possible to denature UF6, so it can be used for reactors for nuclear weapons. I have to caveat that because even remember when I showed you the table where I showed the reactors and with the amount of enrichment you would have to have more and so on. Of course, there's a lot more research that needs to be done on using reprocessed uranium and substituting that in reactors. But my feeling is that it could be used, but then you'd also have to deal with the high radioactivity from this material. My back of the envelope calculation was that unfortunately it's not enough heat to heat the high explosive to trigger or to trigger. So that's one thing you can do, is you can cause it to melt, or you can cause the high explosives to actually trigger, which obviously you wouldn't want to have in an implosion weapon. It seems to me that that's not possible unless you add way more uranium-232, but I need to do more for that. So you have a problem with short assembly times. So for Iran, my Gedanken experiment is possible, but it's expected to be considered, I expect it to be considered discriminatory from their point of view. So where do we go from here? This is a very early study. There's a lot of more work that needs to be done here. We need to determine what level U-232 is actually possible. For that, we have to talk to the people who manufacture this material and process this material. There's a lot of precautions of working with hot fuel, because now it's just going to be basically hot fresh fuel, right? Fresh fuel is not very radioactive, but now it is radioactive, so you have to be able to handle that. And also I was thinking that will this knowledge of working with hot fuel enable work on reprocessing, which is another consideration in the non-proliferation community, of course. And how do we deal with uranium-236? Also, is it possible to enhance impurity, so to introduce impurities into this material that actually cause these extra neutrons if they decide to increase the material to weapons grade, the enriched material to weapons grade? So there might be other things that we can think of. And still need to figure out the fraction of UF6 destroyed due to the alphas themselves. So here what I'm saying is that if you have this U-232 present in the UF6 itself, so that's before you've enriched it, or even when you enrich it, okay? But before you enrich it, if you have a high enough concentration of this U-232, the alphas themselves will destroy the UF6, a certain proportion of UF6. Now what you could do is bubble fluorine or whatever materials to bring it back up to normal level. But through the process, you're actually the alphas are destroying the UF6. So you might consider how can we count for that? Or is that a way of denaturing, let's say? Are there impurities that can be easily removed? So can these impurities actually be removed? So if this is an effect, then in the process, whichever country might want to actually remove the material because they know this, that it's a problem. So how easily can it be removed? I want to conclude by just saying that the advantage is huge to this material, because just as you have this alcohol denaturing, where this vast amount of applications where alcohol can be freely bought in a store and freely used and so on, it would be so great if you could denature regular UF6 so it can't be used in nuclear weapons, but but can be used for reactor fuel. So that's where I want to conclude. Hope I made sense to you guys. It's a crazy idea. So, please ask questions. Yes?
This could be another chemist question. How difficult is it to recalibrate centrifuges to separate 232 from 235?
So people have looked at this, the Russians have looked at this because they want to take out split the U-232 from the U-236 and other elements. In terms of how difficult, I can't tell you, but so some of the reports I looked at have thought about how to tune different cascades. So these are the units in which centrifuges are, so that you could separate one thing and then separate the other, and to try to separate the U-232, which people really don't want. And U-236, they want it in the fuel and separate it out from the rest. So people have looked at it, but I couldn't. I tried to find up-to-date information. I couldn't. It's exactly one of the questions I had. The last report I saw was from 2007, which was an IAEA report, in which was the Russians in particular who had this idea of configuring their cascades in a way to be able to do that kind of separation.
It seems like it wouldn't. I mean, from a layman's view, It seems like it wouldn't be any more difficult than separating 235 from 238.
No, it's possible.
Yeah. One more question.
Yeah.
This goes back to my earlier question. Do I have to stop saying that uranium-238 is not fissionable? Because you said that you get the neutrons from 238 because of the fissioning.
So U-238 is not fissile, but it is fissionable.
Okay,
it does
so
fission.
It's a subtle distinction.
It is a subtle distinction.
And it's a rate difference.
It's the way the cross-section is the curve that I was talking about. It's different for U-238 compared to U-235.
But I mean, is it just slower for 238? Is that the issue that makes it?
No, it's not so much a slowness, it's just the curves are different. So you can't sustain a chain reaction with U-238. That's why you need to U-235.
Yeah. Okay.
I guess this may be a thought experiment of my own, but I think you hit the nail on the head when you're saying you can't single Iran out with this. They're going to go nuts.
Of course.
But is there any way, if there's more study done in this and there's some conclusive findings, that this becomes a new standard for future reactors?
Well, that's the idea. That's the idea.
Right.
Not so much a new standard because that's too grandiose, but at least part of the discussion. So maybe there's other ideas that people will have to introduce something like this. I think denaturing UF6 is important, so that and it would be huge, less expense for the IEA and everybody involved if it was possible to convert the UF6 into material that can't be used for nuclear weapons, but can be used for reactors, even though it's difficult. I think it's worth thinking about.
Could something similar be done? Obviously, plutonium fission's more readily, but can something similar, like an additive of some sort, or what have you, be done to plutonium to make it more proliferation resistant?
There's people who looked at that. There are other ways of doing it, but basically any grade of plutonium can be used for nuclear weapons. If you introduce plutonium-238, remember it has a lot of alphas, then that will produce a lot of heat and will make making a bomb extremely difficult, because you're producing so much heat and you could disturb the high explosives, so it's going to be very difficult. But basically, not really possible, because for a long time people thought that you couldn't make a bomb out of reactor grade plutonium, and that's not the case. Any grade of plutonium you can make it out of.
So with this process, you won't wind up with a P239 weapons grade after the generation process is used.
So that's separate from the oh, I see what you're saying. No. Good question. No, of course you would still produce it.
Okay, so then you
still have a problem with the plutonium. Yes, that's correct. You still have a problem with the plutonium because you still have the U-238 present, and the U-238 is what leads you to plutonium-239. Yes, that's true. So we're just looking at the uranium side. You still need to worry about what happens with the spent fuel when it's been used in a reactor. What happens with the spent fuel, and then it could potentially be processed and the plutonium be separated. Yes.
So that's totally two different technical and policy questions.
Yes.
Then? Okay.
That's right.
I have a simple question, but when you use the term denature, does that mean it's irreversible?
That's the whole point, like proliferation proof or proliferation resistant. Nothing is really reversible. As Mark said, you can always turn on the centrifuges and separate out things in another way, and it's just more difficult. So the idea is to make it more and more difficult. But the idea with the reason why I was thinking uranium-232 is because it's not something that can be chemically removed, right? Because if you separate, because uranium-232 are different isotopes, you can't remove them chemically. You can remove them only by something like centrifuges or something like this. So quiet. Okay. Do you have any questions? Then there you go.